Okay, let's go ahead and get started. Compound probability. That involves events that happen one after the other. A common way for at least me to phrase this is to call them successive events. They happen in succession. One thing happens, and then after that, another thing happens. So it's really common for me to just call these successive events, but compound probability would mean the same thing. One thing happens, and after that, another thing happens. When we're talking about compound probability, we have a success when both things happen. The first thing happens, and then after that, the second thing happens. And one thing that's kind of nice about this structure is it does lean back to the fundamental principle of counting, which you'll remember where find the number of choices for each stage of the problem and then multiply those together. And here what we're going to do is we are going to find the probability of each event and then multiply those probabilities together. So we have multiple things that are going to happen, successive events. We're going to find the probability of the first event, find the probability of the second event, and then multiply those together. Very similar to what we did when we were talking about the fundamental principle of counting. Let's go ahead and take a look at a compound probability type of scenario. A jar contains 5 green, 3 white, and 4 red marbles. A marble is selected, then replaced, and then another marble is selected. So there's our compound probability. We're going to select a marble, and then we're going to select another marble. So we have 2 things that are happening. These are successive events. One thing happens, and then after that, another thing happens. Our probability question says, what is the probability that the first marble is green and then that the second marble is red? What we're going to do is we're going to find the probability of that first event, find the probability of that second event, and then multiply those together. So let's see here. I'll ask you this question, sort of a review from last week, keeping in mind the most important thing about probability is that probability is successes over outcomes. Just the first event right here, the probability that the first marble is green. I'm going to ask you for that. What we're after here overall is, what is the probability that the first marble is green and the second marble is red? So we want green followed by red. My question to you is, what's the probability that the first marble is green? Well, there's something about that that's right, Stephanie, but remember, all probabilities are between 0 and 1. So anything that's bigger than 1 can't be right for a probability answer. All probabilities are between 0 and 1. And there we go. Let's see. To figure out the probability that the first marble is green, I need successes over outcomes. The number of outcomes here is 5 plus 3 plus 4, the total number of marbles in the jar. And so that's going to be 5, 6, 7, 8, and 4. There are 12 outcomes. And of those, 5 are green. So the probability of getting green on that first draw out of the jar is 5 out of 12. 0.42. That's correct also. That's been rounded, but yeah, we're going to leave it as a fraction for now because we're not going to do decimals or rounding until we get to the very end. I'm glad you brought that up, Zara. That's excellent. Okay. Now, according to my instructions here, I take that first marble out. Then it is replaced, meaning I put it back in the jar. So all 12 marbles are still in the jar when I go to draw the second one. And I need the second one to be red. What's the probability that the second one's going to be red? Excellent. Great. And really important you got that one, Stephanie. That's fantastic. Very good. 4 out of 12 right down the line. So 4 out of 12 is the probability that the second one is going to be red. It's important to note that because we replaced the original marble, we still had 12 outcomes. when we went to do the second one. All right, find the probability of the first event, find the probability of the second event, and then multiply those together. Just a reminder, multiplying fractions, we're gonna multiply the numerators together, multiply the denominators together, and we'll have 20 over 144. You could reduce that to what, 10 out of 72 or 5 out of 36, or you can just leave it as 20 over 144. If you're asked for a decimal answer, this is the place where you would figure that out. And you would go ahead and do 20 divided by 144 and end up with 0.14 for a decimal answer. But don't convert these to decimals because you'd be rounding. Wait until you get to the very end, and then if you're asked for a decimal, that's when you go ahead and do the division to find the decimal answer. The key here is with successive events, find the probability of the first thing, find the probability of the second thing, multiply those together. Does anybody have any questions on what we did in that one? The main idea is find each individual probability and multiply those together. I'm going to have you try one if you don't have questions for me. Okay, here goes. A jar contains 5 green, 3 white, and 4 red marbles. A marble is selected, then replaced, and another marble is selected. Find the probability that the first marble is red and the second marble is white. I'm going to set up a poll for this one and have you try it. We'll go another, I don't know, how about 20 seconds, and then we'll do this one together. All right, let's see where we are on this. Unanimous, fantastic, that's great news. Sounds like we've got the idea pretty well handled. That's terrific. So what we're after here is the probability that the first marble is red and the second marble is white. So we want probability of red on the first draw, and that's 4 out of 12. And then let's see, that marble is replaced. So we want the second marble to be white, and there's 3 successes, so that's going to be 3 out of 12. We can multiply those together and have 12 out of 144. We could reduce that actually to 1/12, but we can leave it as 12 out of 144. That's just fine. If you're asked for a decimal, this is where you'd go ahead and do that next step. That went really well. So well, I'm going to have you try another one right away with one little change. Here goes. Same jar, 5 green, 3 white, and 4 red marbles. One marble is selected, and then another marble is selected without replacement. What that means is after the first marble is taken out, we don't put it back in. And then we draw the second marble. So with that in mind, what's the probability the first marble is red and the second marble is white? And I'm going to make a poll for this one and have you try it. We'll see how this goes. The main thing here is, the only difference here is after we draw that first marble out, we don't put it back in. We'll go another 30 seconds on this one. Just be a little bit careful with your, how you're deciding about your successes and outcomes. But the idea is the same. First event has to happen. Second event has to happen also. All right, let's see where we are on this one. Oh, almost unanimous, darn close. We all had the 132 outcomes, so that's good. That's very good. Okay, so when we look at this one, what we're after here is the probability of getting red followed by white, which is the same structure we were looking for last time. The only difference here is we're doing this one without replacement. So when we go to get that red one out first, we have 4 successes out of our 12 outcomes. And then what changes is when we go to get the second marble, now we don't have 12 in the jar anymore. We only have 11. Because we pulled out that first marble and left it out, now there are only 11 marbles left in the jar. And one thing that comes up sometime for students is, well, how do you know the first one was red? Well, that's what this tells us, right? If the first one's not red, then we don't have any successes at all. And we're working to see what is the probability of getting red followed by white. So we're looking at the first one we picked was red. We left it out. Now we're going to see if we get a white one for that second draw to make this thing happen. So we're working towards making this happen. What is the probability of making that happen? So the first one was red. The probability was 4 out of 12. Now we have 11 marbles left in the jar, and of those, 3 of them are white. And so we'll have 3 out of 11 to get a white on that second draw. Find the probability of each event and then multiply those together, and we end up with 12 out of 132. Does anybody have questions on what we did there in that one? Again, the poll went really well, so I'm pretty optimistic. Okay, up next, we're going to look at a couple of other situations that involve successive events, compound probability. The first of those is when percents are involved. Catherine has applied for a job with Globo Corporation. There's a 48% chance she will get an interview. If she gets an interview, there's a 30% chance she will get the job. First, we need to recognize this as successive events. First, she gets the interview, then she gets the job. So those are our successive events. Interview happens, then the job happens. The question just says, what's the probability she will get the job? Well, she's not going to get the job without the interview first. So what we're after here is the probability of getting an interview and then getting the job. And you don't have to write it out that formally. I just kind of did that to emphasize the idea that this problem is very much like what we were looking at with the marbles in the jar. We need one event to happen, and then after that, we need another event to happen. Okay? Here, we don't have a list of successes and outcomes, which at first might be a little unnerving, but in reality, this one is much simpler for us to do. There's a 48% chance she will get the interview. So the probability of getting an interview is 48%, which we'll write as a decimal. And then if she gets an interview, there's a 30% chance she'll get the job. So after the interview has happened, now there's a 30% chance you'll get the job. We don't know successes and outcomes. We already know the probability is 30%. And we'll write that as a decimal, 0.3. So here, the probability that she was going to get an interview was 0.48. The probability she was going to get the job after that was 0.30. We'll multiply those together to find the probability that she's going to end up with this job. 0.48 times 0.3 is 0.144. And if we were going to round that to the nearest hundredth, Let's see, we'll find the hundreds place, look one space to the right, that's 4 or lower. So we would round this down to 0.14. A problem like this would ask you to have the probability written as a decimal, so you wouldn't have to go any further than that. At first glance, you might think, I don't know the successes and the outcomes. What am I supposed to do here? Just remember, these turn out to be much simpler than that. We already know what the probabilities are. We just need to make sure we multiply those together. Any questions on that one before we look at one that's kind of similar? Okay. This time we're going to look at a successive event situation that involves fractions. There is a 2/7 chance that Natalie will go to the grocery store today. When she goes, 3/5 of the time she spends over $50. So we can see our successive events in here. She might go to the grocery store, and if she goes to the grocery store, she might spend over $50. So those are our successive events. First, going to the grocery store, and second, spending over $50. Here again, you don't have to be this formal about it, but going to the store and spending over $50. That's what we're looking for. First event is go, second event is spend over 50. Our question is, what is the probability she spends over $50 at the grocery store today? And so in order to spend over 50, she would first have to go. So both things are built into this one question, kind of like they were last time with Catherine and the job. In order for her to get the job, she would have had to do the interview first. Here, in order for Natalie to spend over 50, she would have to go to the store first. So two things have to happen: go to the store and spend over 50. All right, well, going to the store, let's see, successes and outcomes. Well, I don't have successes and outcomes written down, but I've been given the probability. There's a 2/7 chance that Natalie will actually go to the grocery store. Okay, well, so the probability of her going is 2/7. And then if she does go, 3/5 of the time, she spends over $50. So if she's at the store, the probability she'll spend over $50 is 3/5. The probability that she goes, the probability she spends over 50, and we'll multiply those together. We'll multiply our numerators. 2 times 3 is 6. Multiply our denominators. 7 times 5 is 35. So the probability that she's going to spend over 50 at the grocery store today is 6 out of 35. We could convert that to a decimal if we were asked to, but 6 out of 35 is okay here. We weren't told that we needed to do that. Any questions about those two? I think the thing with those two is it almost feels like this can't be all there is to it, when in reality it is. If you're given percents that are the probabilities, you're just going to convert those to decimals and use those as the probabilities in your question. And here, if you're just given the probabilities as fractions, that's okay. Go ahead and use those probabilities when you go to find your compound probability. So far, we've kind of talked about the idea of compound probability, and one thing happens, and then after that, another thing happens. Everything we've looked at so far has been after a single specific outcome. Here's what I mean by that, just sort of backtracking a little bit. When we did this first question, it was green followed by red. Single specific outcome, green then red, that's it. Nothing else would be a success. We had red followed by white, that's it. Red followed by white, that's it. That's the only possible success here. We had red followed by white again. Here we had get the interview, get the job. That's the probability we were looking for. And here we had go to the store, spend over 50. Single specific outcome. Sometimes we won't be after a single specific outcome. There might be more than one way to have a success. When that happens, that's when we bring tree diagrams into our toolkit of how do we solve this? We use tree diagrams. Tree diagrams are a great way to organize complex situations, and they're a great way to answer questions that might be after more than one single specific outcome. And I'll make sure that I differentiate between what is a single specific outcome and what's not. Because you're going to want to know, when do I need to use a tree diagram anyway? And I'll make sure that we discuss that. So tree diagrams are what we're going to talk about next, and they are fantastic if the situation's fairly complex or if we are not after a single specific outcome. Because if we are after a single specific outcome, we just need to find the individual probabilities and multiply them together, and that's it. Sometimes it's a little more involved. First, let's look at the whole idea of what is a tree diagram anyway. And what a tree diagram is it gives us a way to find our sample space and see all the possible outcomes for a situation. So parents are going to have two children. Create the tree diagram for this situation. So for right now, we're just looking at what is a tree diagram and how do you make one. So these parents are going to have a first child, and that child's either going to be a boy or a girl. When we make a tree diagram, we start out with nothing because nothing has happened yet. So we start out with nothing. And then that first child's born, it's either a boy or a girl, and there we go. Now, one of the things we'll do with the tree diagram that'll be really useful for us is we're also going to put the probabilities right here on our diagram. Probability of having a boy is 1/2. Probability of having a girl is 1/2. This particular tree diagram won't be that interesting. We're keeping it real simple here at the beginning. We'll get more complicated and more interesting later on. For right now, we're going to keep all our probabilities very simple. Okay. Now they're going to have another child because they're having two. And this is where tree diagrams sometimes get complicated for students. So I need you to hang in there with me on this for just a minute. What's going to happen is we're going to write down all the possibilities that could happen. So if the first child is a boy, then we're up here. And that second child is either going to be a boy or a girl. So it's important for me to have you realize that this child right here is the second child after the first child was a boy. We also have to account for a second child if the first child was a girl. And we're going to put that down here. If the first child's a girl, the second child can either be a boy or a girl. Sometimes students who are new to tree diagrams look at this and say, but it looks to me like they're having 1, 2, 3 children. The problem said they're only having 2. How is this 3? And it's a good question when you're first getting started with tree diagrams. But here's the thing. The first child is right here. It's either a boy or a girl. And then the second child is all of this. And the reason that that column right there represents the second child is because this is the second child if the first child was a boy. This represents the second child if the first child was a girl. And so this entire column right here represents the second child. So while it kind of looks like there's 3 things there, really it's only 2, because what's going on over here is dependent on what happened with the first one. Please let me know if you see more than 1, 2 children here so that we can make sure we iron that out before we go forward. Okay, perfect. We need to put the probabilities on there too. And the thing about that is boy or girl is always just going to be 1/2. That's why I said this isn't going to be the most interesting tree diagram. All the probabilities are the same. So parents are going to have 2 children. Create the tree diagram for this situation. And we've done that. What we can do here is we can see everything that could possibly happen. We can see all the outcomes. And what we're going to do next is we are going to write down our sample space and all the probabilities that go with them. So this tree diagram is really just a tool for us to get to our sample space with the probabilities. And here's how we do that. If I follow this path and this path, I had boy followed by boy. So the outcome, if I end up here, is boy followed by boy. And the probability of that outcome is what I get when I multiply the probabilities along that path. Successive events, one thing happens, then another thing happens. The probability of a boy was 1/2. Probability of a second child being a boy was 1/2. So we multiply those together. And the probability of boy followed by boy is 1/4. Let me know if you see anything that you're unsure of, uncomfortable with, or doesn't make sense. We're going to do this with every outcome along the whole tree. I could have boy followed by girl. Okay, so that's boy followed by girl. And the probability is what I get when I multiply the probabilities along that path. 1/2 times 1/2 is 1/4. We're building a whole sample space, so we're going to do this with every possible path. Now we have girl followed by boy. So we have girl followed by boy, and that's multiply the probabilities along that path, successive events, multiply the probabilities together, 1/2 times 1/2 is 1/4. And then finally, at the very bottom, we have girl followed by girl, which is 1/2 multiplied by 1/2, which is also 1/4. What we've done now is we have created our sample space and we know all the probabilities. At this point, we're kind of done with the tree. The tree was there to serve a purpose, and it was to get us to here, to get us to this. Now I have my sample space and I know the probabilities of everything that could happen. Please note that boy girl is not the same as girl boy because they happened in a different order. In my family, we had the boy followed by the girl. From what I understand, if you have the girl first, she actually helps with the second one. That wasn't necessarily the case with us having the boy first. At any rate, this is our sample space here in this box, and we have all the probabilities. Now, what this is going to be useful for is answering questions. And here's the type of questions we're going to see. Parents are going to have 2 children. Find the probabilities for the probability of 2 boys, the probability of exactly 1 boy, and the probability of at least 1 boy. So those are the types of questions we can answer with our tree diagram. One thing I want to point out, the probability of 2 boys. This would be the probability of boy followed by boy. That's a single specific outcome. We wouldn't necessarily need a tree diagram to answer that question. We could do that one without the tree. Since we have the tree, let's go ahead and look at it anyway. So the probability of getting 2 boys. So we go back and we look at our sample space here and we see that this is the only place where there's 2 boys. And so the probability of getting 2 boys is 1/4. So the probability of getting boy followed by boy is 1/4. Okay, now we get into the types of questions that are not looking for a single specific outcome. For these types of questions down here, we need that tree diagram because the probability of exactly 1 boy, well, there might be more than one way to do that. There's not a single way to do that. So now we need our tree diagram, which gives us our sample space. So the probability of getting exactly 1 boy. We go back and we look at our sample space. We say, okay, exactly 1, no more, no less. This is boy followed by boy. That's 2 boys, that's no good. Boy, girl, that's exactly 1 boy, that works. Girl, boy, that's exactly 1 boy, that works. Girl, girl, there's no boys there, so that's no good. So there's more than one way to have a success. When I'm looking for exactly 1 boy, I could do it this way or this way. There's more than one way to have a success here. boy, girl, or girl, boy. And so what I need to do when I find that there is more than one way to have a success, I need to add those probabilities together. I need to say 1/4 plus 1/4, that would be 2/4. Add the numerators, keep the denominator the same. We wind up with 2/4. So the probability of getting exactly one boy, probability of exactly one boy is 2/4. I'm going to back up just a second before we do the next one. Sometimes students will ask the question, okay, wait a minute. Sometimes we're adding, sometimes we're multiplying. How in the heck am I supposed to keep that straight? Totally fair. Here's the thing. We multiply when we have one event after another. When we're walking along these paths, we multiply. When I go, this has to happen, and then after it, this has to happen. These are successive events. I multiply those together. And I do that all the way down the tree diagram, multiplying those probabilities together. Once I've created my sample space, I'm done multiplying. That's it. I'm done multiplying. The multiplying part's over once I've created my sample space. Now that I have my sample space in place and I look it over and I say, okay, I've got my sample space. Now, if there's more than one way to have a success, like there was in this problem, I could have a success this way or this way. I need to join those together. And when I join those together, I need to add them. So if there's more than one way to have a success, that's when we do the adding. Hopefully that helps clear that up a bit. Let's look at that third question that we had on the other page. And just to sort of help us out with that, our sample space was boy, boy had a probability of 1/4. Boy, girl had a probability of 1/4. Girl, boy had a probability of 1/4. And girl, girl had a probability of 1/4. And the last question we've got here says, what's the probability of at least one boy? So I go over to my sample space that, remember this, I've just recopied this over. It came from our tree diagram. We have our sample space. I want the probability of at least one boy. Well, at least one boy means one or more. So let's see. Boy, boy. Yeah, that has at least one boy. Boy, girl. Yep. Girl, boy. Yeah, there's a boy in there. Girl, girl. No, that's no good for this one. So the probability of at least one boy, I could get at least one boy this way, or this way, or this way. So I need to add those all together. 1/4 plus 1/4 plus 1/4. The probability of getting at least one boy is 3/4. That's how we build a tree diagram, use it to get a sample space, and then use that sample space to answer questions. If we're looking at a problem that has one single specific outcome, we don't necessarily need to use the tree. We can. If you love the tree, you absolutely can use it. But then there will also be questions that, well, there might be more than one way to have a success. When that happens, we need the tree diagram, we need the sample space in order to arrive at those probabilities. Okay, before we look at a much more interesting situation, I want to give you a chance to ask me any questions that you might have about that tree diagram discussion we just went through. Okay, all right. Let's do one with some more interesting probabilities on it. A jar contains 6 blue and 2 yellow marbles. 2 marbles will be drawn, one after the other, without replacement. Create the tree diagram for this situation. And we'll do this one together. I'll give you a chance to make one on your own in a little bit. First, we're going to do this one together. So, all right. So I'm walking up. I'm going to draw a marble out. And the first one I pick is either going to be blue or yellow. So blue or yellow. Now I'm going to ask you, what's the probability of getting a blue one on that first draw? Careful, Madison. All probabilities are between 0 and 1. So very good, Zara, Lorraine. We have 6 blue ones and we have 8 total outcomes. Probability of successes over outcomes. So the probability of getting a blue there is going to be 6 out of 8. And what's the probability of getting a yellow on that first draw? Excellent, Genesis. Lorraine, Natalie, thank you. 2 out of 8. Very good. Okay, so there's our first draw out of the jar. We have the probabilities on our tree. Now we need to do the second draw. And if I'm up here, it means the first one was blue, and the second one could either be blue or yellow. If I'm down here, it means the first one was yellow, and the second one can either be blue or yellow. Putting the probabilities on here is probably the single thing that might trip you up. Remember what we've done here. We're doing this without replacement. And if I'm up here, it means the first one that I took out was blue. So I started out with 8 marbles in the jar. I drew a blue one, and I'm leaving it out. So now when I go to get this blue one up here, we need to think about how many are left in the jar. What's the probability of getting a blue one? So what is the probability of getting a blue one here? And I don't think this is an easy question. Outstanding. Very good, everybody. That's terrific. You're exactly right. There are 7 marbles left in the jar, and we started with 6 blue. We took out a blue, so there's only 5 blue ones left. So our probability of getting a blue there is 5 out of 7. Excellent. Outstanding. Okay. Following that same logic then, after I've gotten a blue one, what's the probability of getting a yellow one here? So I drew a blue one, I left it out. What's the probability of getting a yellow? All right, very good. Natalie, you're close there, but remember, if we're up here, that means the first one we took out was blue. So both yellows are still in the jar. So I have 2 yellows out of 7 marbles. So the probability is 2 out of 7. And it's great when you guys answer because it's great when you answer and maybe you make a mistake, right? Like that. Now it's great because we get a chance to talk about that. If we just do it right all the time, all the way through, then something that somebody's thinking doesn't get addressed. So it's great when you mention it, even if you're throwing out there and it's not the right thing. That gives us a chance to talk about it, and that's awesome. Okay. Back down here to the bottom, we need these probabilities also. And so now if I'm down here, that means the first one I drew out was yellow. So, and remember, we started all over. We drew out a yellow one. So after drawing out a yellow one and leaving it out, what's the probability of getting a blue one? Again, I don't think this is an easy question, but so far you guys have done great and you're still doing great. That's fantastic. You're exactly right. There are 7 marbles left in the jar. We started with 6 blue. We took out a yellow. So all 6 blue are still in there. And then we got a yellow. What's the probability of getting a yellow one after that? Perfect, Madison. Yes, Stephanie, that's right. We have 7 in there. There's only 1 yellow left. I started with 2 yellows. I took out a yellow. So there's only 1 yellow left. Outstanding. We've built our tree. We're going to answer some questions about this. So we want to go ahead and figure out what our sample space is going to be and what the probabilities are that go with every possible outcome. And so as we go through this, let's see here, we've got blue followed by blue, and we'll multiply the probabilities along that path. More interesting probabilities than we had before. Let's see, 6 times 5 would be 30, and 8 times 7. You know, there's just some that are not always easy to memorize. 8 times 7 is 56. All right, so the probability of blue followed by blue is 30 out of 56. If you're thinking, how can there possibly be 56 different outcomes? Well, we started out with 8 marbles in the jar. On the second draw, there were 7 possibilities, and we all know the fundamental principle of counting. Number of possibilities on the first pick, number of possibilities on the second pick. Multiply those together, there's going to be 56 total outcomes, and that's what we see here in our sample space. Okay, up next we would have blue followed by yellow, and that'll be 6/8 times 2/7. Be careful when you do these. It's really easy to grab the wrong numbers or make a mistake that way, so just be patient and careful as you go through them. 6 times 2 would be 12, and 8 times 7 is still going to be 56. All right, and we keep going through, and we have yellow followed by blue. So yellow followed by blue, that's 2/8 times 6/7. So 2 times 6 will be 12, and our denominator is going to stay 56. That's kind of nice. And then finally, we have yellow followed by yellow. We'll multiply those two probabilities together because we're getting a yellow one. Then after that, we're drawing a yellow one. These are successive events, one after the other. That's why we're multiplying. And 2 times 1 is just 2 out of 56. At this point, we have our sample space. Our tree diagram has served its purpose. It got us to our sample space. And just sort of a mental note, we're done multiplying. We may need to add some probabilities together depending on what questions we're asked, but we're done with the multiplying part. That's over. Let's go see what kind of questions we're supposed to answer about this one. 2 marbles drawn, one after the other without replacement. What's the probability that they're both yellow? Well, probability that they're both yellow. Because that is a single specific outcome, I wouldn't necessarily need a tree for that, but we've already done it. So we might as well just go look. And we go back and we look at our sample space and we see yellow followed by yellow is 2 out of 56. So the probability that they're both yellow is 2 out of 56. The next question says, what's the probability of at least one blue? And at least one blue, now this is not a single specific outcome. We would need the tree for this. Luckily, we've already done it. We've already done our tree. We need the probability of at least one blue. So we'll go back and we'll find those outcomes that have at least one blue. Well, this has at least one blue, at least one or more. This has at least one blue. This has at least one blue, and this does not. So I could get at least one blue marble this way, or this way, or this way. So we need to add all those together. We're going to add all those together, and that'll be, let's see, 30 over 56 plus 12 over 56 plus 12 over 56. We'll add those together and have, let's see, 30, 42, 54 out of 56. Almost a certainty. Very likely that we're going to get at least one blue. The probability of at least one blue was 54 out of 56. There's one more question on this page that we haven't done yet. And for that one, I'm going to set up a poll. What is the probability that the second marble is yellow? I'll set up a poll for this one. And I can go back to that sample space page if you want me to. Probability that the second one is yellow. Although you probably have it written down. Yeah, so the probability that the second marble is yellow. Oh, sure thing. Yeah. Oh, shoot. I lost my poll. Dang it. I was afraid of that. So going off the page, we lost our poll, but I was able to see a lot of results came in. You can let me know um, if you have questions about it when we talk about it. And it's not your fault, Lorraine. I wasn't sure if that would happen or not. I should have. No, it's totally fine. It's totally fine. All right. So let's answer that question. Um, we don't get to see the poll results there, but please let me know if you have questions about it. You know what? I'm going to put it back up. I'll just put it back up and then we'll get to see those results. So, um, probability that the second one is yellow. There we go. Let's just have a do-over with that. So nothing's changed. It's the same question, same answer. What's the probability the second one is yellow? We'll go another 20 seconds, or how about, yeah, we'll go 20 more seconds and then we'll talk about it. All right, let's see where we are on this one. Okay, not unanimous, but definitely strong agreement. That's really good. Really good. Tree diagrams can be a tough topic. And so knowing how to take that sample space and answer a question with it is really important. And and it looks like we're in a pretty good place. If you see something you're not sure of, you let me know. What we're after here is the probability that the second one is yellow. So what we need to do is go identify our successes. So blue followed by blue. Nope, the second one is blue, so that's no good. Blue followed by yellow. Yep, the second one was yellow. Yellow followed by blue. There's a yellow one in there, but it was first. So nope. Yellow followed by yellow. Yeah, the second one's yellow, so that's a success. So I could get the second one yellow this way or this way. So I need to add these together. And 12 out of 56 plus 2 out of 56 will be 14 out of 56. Let me know if you have questions about how we arrived at that answer. Up next, I'm going to let you try one start to finish. Okay. An ice chest contains 9 cans of ginger ale and 5 cans of orange soda. 2 cans will be drawn, one after the other, without replacement. Find the probability of getting exactly 1 orange soda. As soon as we read this question, probability of exactly 1 orange, this is not a single specific outcome. There might be more than one way to do that. So I need a tree diagram. I'm going to make a sample space, and then I'm going to answer the question. All right, I'm going to give you some time on this to draw the tree, come up with the sample space, and then answer the poll. If you're really comfortable with that at this point, that's fantastic. If you struggle making the tree, that's okay. We're going to do it together, and then I'll give you a chance to answer a couple more questions about this same situation. I want you to try to draw the tree and answer this all the way start to finish. If you get stuck somewhere along the way, make sure you ask questions when we do it together. All right, I'll give you some time to do this, and I'll set up the poll. Don't feel like you have to rush through this one, but I do want you to try it. This is definitely the type of question you can expect to see um, in our homework, on a quiz, on an exam. As you finish this one up and as we go through it together, I will say that um, this is as challenging of a question as you'll see today. And some people would say this is the most challenging type of question in Math 123. So if you feel really confident about this and you're getting comfortable with this, then you're in a really good place. If you are struggling a little bit, it's completely understandable. The first time you saw this was, less than an hour ago, and um, and there's a lot going on in a question like this, and it might just take some practice and some time. So don't put too much pressure on yourself. But if you are able to solve these, then that's fantastic. I'm thinking we'll go another 30 seconds, then we'll draw the tree diagram and answer this question together. All right, let's take a look and see where we are. Okay, outstanding. Very good. Strong agreement on this one, and we're going to talk through it, and you let me know if you have questions. Wow, that's really good. I wasn't sure if I was going to have you draw the tree or if I was going to draw it first. I think letting you draw the tree was the right thing, given how well that turned out. Okay, so our first can that we pick is either going to be ginger ale or orange, and we need the probabilities that go with those. We have 9 and 5, so there are 14 total outcomes. And the probability of ginger ale is 9 out of 14, and the probability of orange is 5 out of 14. If you see something that doesn't make sense or you're not sure where it came from, don't hesitate to let me know. All right, first one I got was ginger ale. The second one will come up here as ginger ale or orange. And those probabilities, let's see. I started with 14 cans. I took out a ginger ale. So I have 13 cans left, and 8 of those are ginger ale. I started with 14 cans. I took out a ginger ale. There are 13 cans left. All 5 orange are still in there. So 5 out of 13 for orange. Now I've got to do the bottom half, where if the first one I got was orange, the second one's either ginger ale or orange. Okay, let's see. So first one I got was orange, so there's 13 cans left. All of 9 ginger ales are still in there. First one I got was orange. There's 13 cans left, and I had 5 orange to start with. I took an orange out, so there's only 4 orange left. So I built my tree. Let me know if you have questions about how any of those numbers came about. Now I'm going to find my sample space. Ginger ale is going to be 9/14 times 8/13. Wow, I don't know if the numbers need to be this interesting all the time. 9 times 8 would be 72 out of 14 times 13 is 182. Okay, whatever. 72 out of 182. That's what it is. Fine. Ginger ale followed by orange. 9 times 5 would be 45, and the denominator is going to be 14 times 13 every time. Then orange followed by ginger ale is 5/14 times 9/13. 5 times 9 can be 45 and 182 on the denominator. And then orange is 5/14 times 4/13. That'll be 20 out of 182. Now I've got my sample space. I'm ready to answer questions. And an important thing to note is now I'm done with any multiplying. Multiplying's over. I've done my successive events part. Now I just need to answer questions. And the question here was, what's the probability of exactly 1 orange? Well, there's no orange there. Ginger ale, orange. Yep, that has exactly 1 orange. Orange, ginger ale. Hey, this has exactly 1 orange also. This has 2 orange. That's no good. So there's 2 ways I could get exactly 1 orange. I could get the orange first, or I could get the orange second. So I could get exactly 1 orange this way or this way. I need to add those together. 45 and 45 will be 90 out of 182. Let me know if there's anything in there that you're unsure of, didn't make sense. How'd you get that number? Why'd you add those together? And it's because we could have exactly 1 orange in this outcome. We also have exactly 1 orange in that outcome. And so we need to add those together to get our total number of successes, which is 90 out of the 182 possible outcomes. All right, let's try another question. Same setup, same tree diagram. What is the probability of at least 1 ginger ale? I'll set up a poll for this one. The probability of getting at least 1 ginger ale. Same tree diagram, same sample space. Now the question is, what's the probability of getting at least 1 ginger ale? And so once you get to the point where you've drawn your tree, you've found your sample space, now it's just about being very careful when you read the question and make sure you identify all the successes. We'll go another 20 seconds on this one and then talk about it. Now let's see where we are on this. Wow, outstanding. You guys are doing a fantastic job with this today. I'm impressed and thrilled both. So the probability of at least 1 ginger ale, we go back and we say, all right, well, I have at least 1 ginger ale here. I have a ginger ale here. I have a ginger ale here. I don't down here. So I could get at least one ginger ale this way, or this way, or this way. So I'll need to add all those together. And let's see, 72 plus 45 plus 45 is 162 out of 182. So the probability of at least one ginger ale is 162 out of 182. How are we feeling about the tree diagrams? I get a sense that we're doing great. So let me know if you have questions. There is another tree diagram question I want to look at with you. It's a little bit different, and I think it's kind of a fun one. Okay, Lady and the Tiger. I don't know if you know the story of the Lady and the Tiger, but basically what happens is there's a prince, and he's trying to rescue the lady. And what's going to happen is that a lady is going to go in one of these two rooms, and a tiger is going to go in the other one of these two rooms. And the prince gets to decide. He can see the map, and he gets to say, I want the lady to be well, I guess he doesn't get to see the map. That wouldn't be fair. Then he'd know where to walk to. But if you were the prince, forget that you get to choose, take that part out. If you were the prince, which room would you want the lady to be in based on the probabilities here? And so that's what we're looking at here, is essentially the probability of ending up in room number 1, the probability of ending up in room number 2. Don't make this harder than it is. Essentially what we've got here is a tree diagram in the form of a map. So when we get here, there are 3 possible directions you could go. Madison's on top of it. All right, and if we say the probability of this way is 1/3, the probability of this way is 1/3, and the probability of this way is 1/3. It's random. We're not going to psychology in this to see what happens. And okay, if you take this path and now you're up here at this decision point, you could go this way or this way. There are 2 possibilities. So the probabilities are 1/2 and 1/2. This one, you just walk straight in the room, that's it. If you take this road down here, then you get to another decision point, and there are 3 possibilities. So that's 1/3, 1/3, and kind of hard to write it on there. We'll just put it right there as 1/3. And so now what we have to do is look and see the possible outcomes, right? So we could go this way and this way. That'd be 1/3 times 1/2. So the probability you come out that entrance would be, let's see, 1/6. And then the probability of doing this is 1/3 times 1/2. That's 1/6. The probability of this, you don't have to multiply anything. That's just 1/3. And 1/3 times 1/3 would be 1/9. Let me know if any of these numbers don't make sense or you're not sure of them. 1/3 times 1/3 would be 1/9. And then 1/3 times 1/3 would be 1/9. Oh, because there's 3 possible choices. So when you're here, you could go up, you could go straight, or you could go down. And so each one of those gets a probability of 1/3. And here you could go straight or you could go down. There's 2 choices, so it's a 1/2 on each. And when you're at this point, you could go up, straight, or down. So each one of those gets a 1/3 because there's that many possible choices. Now what we've got to do, and part of the reason I like this question so much is now we have to, oh good, very good. I'm glad you asked, Madison. That's great. Now we have to figure out the probability of going in each room. The probability of ending up in room number 1 would be this plus this plus this, because you could end up in room number 1 this way, or this way, or this way. And so room number 1, we've got 1/6 plus 1/3 plus 1/9. And as somebody who teaches math for elementary teachers, I love this because now we have to remember back to 122 and working on fractions, and we need a common denominator. Let's see, what's something that 6, 3, and 9 will all go into? What am I going to use for a common denominator? That would be a common factor, Carolina. All right, Genesis with the 18, because 9 would be okay, but 6 won't go into 9. So that doesn't work. We need something that all three of them will go into, and that'll be 18. So we're going to rewrite these with 18 as our denominator. So now we want to write equivalent fractions. If we multiply the denominator by 3, we multiply the numerator by 3. Always nice to review fractions. If you're a little rusty, that's okay. But it makes it fun for me. If we multiply the denominator by 6, we have to multiply the numerator by 6. And what we're saying there is that 1/6 has the same value as 3/18. 1/3 has the same value as 6/18. And then multiply denominator by 2, multiply numerator by 2. And now that they have a common denominator, we can add those. 3 and 6 is 9. That will be 11 out of 18 is the probability of ending up in room number 1. Now let's look at room number 2. For room number 2, let's see, we could get in room number 2 this way, or this way, or this way. And so we need to add 1/6 plus 1/9 plus 1/9. 18 is going to work for a common denominator again. And multiply denominator by 3, so multiply numerator by 3, denominator by 2, denominator by 2. And we add 3, 4, 5, 6, 7. So the probability of ending up in room number 2 is 7 out of 18. So if you are the prince, you would rather have the lady be in room number 1, because at random, you have a better chance of ending up in room number 1 than you do in room number 2. I think it's a cool question. Not only does it bring in basic probability, we could go any of 3 directions, so they all have a probability of 1/3. We go 2 directions, so they each have a probability of 1/2. We could go 3 directions, so they each have a probability of 1/3. Then we do successive events. If I go this way followed by this way, I need to multiply those together to get the probability I come out of that door. And if I go this way followed by this way, I need to multiply those probabilities to get the probability I come out that door. So we have basic probability, we have successive events, and then we get to review fractions, which is always great. Okay. Any questions about what we just did on that one? There's a lot going on there, I guess. More than I thought when I threw it in there for today. Okay. A couple of notes about the homework from this section. There's problems from the book, and there's also a worksheet. Anytime you're working on a probability question, keep the most important thing in mind. Probability is successes over outcomes. When we're asked to find a probability, we're looking for successes over outcomes. There might be a lot of different ways to get there. Maybe it's just a probability question. Maybe it's successive events looking for a single specific outcome where we just find the probability of each event and multiply them together. Maybe it's more involved than that. Maybe it's at least one ginger ale, or the second marble is yellow, or exactly one orange soda. Maybe it's one of those type of questions that we're going to need to make and use a tree diagram. Just be patient, be careful when you make your tree, get your sample space, and then make sure you identify all the successes that are in that sample space when you go to answer the question.